Welcome to the 7th lecture on Approximation Algorithms. Today we will talk about the problem of scheduling jobs on parallel machines, and for that we will combine techniques from ILPs and parametric pruning, both of you already know. So let's start with the problem definition. We have a set of jobs and we have a set of machines. And for every job we know how long does it take to do this job on a machine. So for any machine and any job, we know the processing time, Pij, of this job on that machine. And now the problem we want to solve is, of course, we want to assign the jobs to the machines, and we want to optimize something. So there are several things you may want to optimize. The one that we look at here is the make span. So we want to find a schedule of the jobs on the machines where the total time to completion is minimized. So the maximum time that a machine is in use. Let's have a look at this example here. We have 3 machines, so we can plot them like this. And now, for example, to machine 1, we assign the jobs 1, 3, and 8. To machine 2, the jobs 2 and 7. And to machine 3, the jobs 4, 5, and 6. Now the length of these boxes tells us how long does it take for this job to run, and the make span now is how long does the longest machine take. This is this one here, so this is the make span of this schedule. This is, for example, something that you want to use on processors when you have parallel cores and you want to assign the jobs to the cores, or even if you want to produce stuff and you have several machines and you want, of course, to spend as little time as possible in total to produce everything. So this is a quite natural problem. First, we want to find an ILP formulation for this. And this is something that I want to give to you. Try to find the ILP formulation first for this problem here. So what we want to minimize is the make span, so we use one variable t. Then what are our variables? Well, what we can do is we can assign these jobs to machines. So we want some variable that tells me that job j is assigned to machine mi. So we need some variables xij that tell us it is 1 if the job is assigned to the machine and 0 if it is not. What are the constraints? Well, every job we only want to assign to one machine, but to exactly one machine. That's what we have to make sure. So we have to make sure for every job that it's assigned somewhere. And then we also need some constraint for the machine, because we want to minimize the make span. And with some constraint, we have to tell this variable how large it is. So let's start with the jobs. The sum of the assignments of jobs to machines is exactly 1. It's on exactly one machine. And now for every machine, we can figure out how long does this machine have to work. And if we look at all of those, then it gives us the make span. So for every machine, we sum up over all the jobs that are assigned to it, multiplied by the processing time. And that gives me the time that this machine I takes to complete its jobs. And if we make sure that t is at least as large as all of these, so for every machine t is at least as large as however this long this machine takes, then t is the make span because we minimize it. It could theoretically be that t is larger if we have some valid solution, but it cannot be smaller than the processing time of a single machine. And since we want to minimize, it will be as small as possible, so it will be exactly the same, the make span. The next task I have for you is I want you to prove that the integrality gap of this ILP is unbounded. And for that, you have to find an instance where the optimum solution in the ILP is by some unbounded factor larger than the optimum solution of an LP. And there is one very simple example. We have m machines and we have one job that has processing time m. Now in the ILP we have to assign it to exactly one machine, and then this machine will take m time. So the make span in the ILP is m. But in the relaxation in the LP, we can assign 1 over m of this job to every machine. So then the processing time in total, or in the make span, is only 1. And we can make this as large as possible, so we have an unbounded integrality gap. That means that without some extra tricks, there is no chance for us to use the relaxation to give us a good solution. But we know some additional extra tricks. We know the parametric pruning. And the parametric pruning we now want to apply to this ILP. So we want to strengthen the ILP by adding some implicit constraints. So if we know how big the make span is, then we know if there's some job that takes more than this on the machine, then this cannot be in the optimum solution. So we can be sure that all those job machine assignments that are larger than the make span, for those the variable has to be 0 in the optimum solution. And this is what we also did in the parametric pruning in the previous lecture. We guessed what is the optimum solution, and everything that was larger we just throw out. Of course, again, we don't know the make span before, so we have to figure out some bound on the make span. So we want some new parameter, that's a capital T, that estimates a lower bound on the optimum. And for some parameter T, we can define all those pairs of machines and jobs that could be in the optimum solution here. So where the processing time of job J on machine I is less than or equal T. And if we have estimated this T, then we can get a relaxation that is pruned. So we can take our ILP, we can prune it, and we can relax it. How do we do that? First we want to relax. That means we have to get rid of the integer constraints, and we just say this is greater than equals 0. Then, for some of these values we already know that they have to be 0, which are exactly those that take longer than t. So this only has to hold for everything in the set st. Now only these are our variables that are left. All the others we can completely throw out. What about the other constraints? Well, we don't have to do this for everything, but again, only for the pairs that are still in our set that we want to look at. And we have to make sure that this is not larger than our capital T that we guessed. And now we don't even need the minimization anymore. We don't have this small t that gives us the make span. We just want to figure out if there is any solution where we have guessed this make span. So in a very short way, this is the linear program that's left. And the interesting thing here now is this doesn't even have an objective function. We only have to determine if a feasible solution exists. So if we guess the make span and we figure out, yes, there is a solution with this make span, then we already know how large the solution is. So the capital T immediately gives us our objective value. But the question is, why does this relaxation give us a good integrality gap? And that's what we want to analyze in the next few parts.